Today, we're going to take a deep dive into how marijuana actually impacts the brain and the body, and I say actually because there's a lot of mythology and misunderstanding around this topic. We'll look at the neuroscience of how THC and CBD interact with the brain's endocannabinoid system, what that means for things like mood, memory, and motivation, and how marijuana use can affect everything from sleep to hormone regulation. My goal here isn't to tell you whether marijuana is good or bad, rather, it's to give you the scientific framework so you can understand the mechanisms involved and make informed decisions about its use. By the end of this talk, you'll know which brain circuits are affected, why some people experience relaxation while others feel anxiety or paranoia, and how both acute and long-term use can impact your health and performance. The endocannabinoid system is a network of receptors signaling molecules and enzymes found throughout the brain and body that helps regulate critical functions like mood, appetite, pain, memory, and stress. It is called endo because it is produced within the body naturally, and cannabinoid because it was discovered after scientists studied how cannabis interacts with these pathways. Two primary receptors in this system, CB1 and CB2, are located in different parts of the nervous system and immune system. CB1 receptors are especially concentrated in areas of the brain that govern memory, emotion, decision, making, and motor control, such as the hippocampus, amygdala, prefrontal cortex, and basal ganglia. CB2 receptors are found primarily in immune cells and peripheral tissues, where they help regulate inflammation and immune responses. Together, these receptors and their natural ligands create a fine-tuned system designed to keep the body in balance, a process known as homeostasis. When marijuana is consumed, the main psychoactive compound THC binds to these CB1 receptors in the brain, essentially mimicking the body's own endocannabinoids, but doing so in a more prolonged and amplified way. This is why marijuana has such noticeable effects on perception and mood. The hippocampus, a brain area crucial for forming new memories, is heavily affected by THC binding, which is why people often experience short-term memory lapses when high. The prefrontal cortex, responsible for planning, impulse control, and executive function, also receives strong input from THC, which can temporarily alter judgment and decision-making. At the same time, activation of CB1 receptors in the basal ganglia and cerebellum influences movement and coordination, which explains why reaction times slow down after cannabis use. Another key effect comes from THC action in the amygdala, the brain's emotional processing center. For many, this produces a sense of relaxation and reduced stress, but in some individuals it can heighten fear or anxiety, leading to feelings of paranoia. This difference often comes down to genetics, prior experience with cannabis, and the specific THC concentration in the product being used. The nucleus accumbens, part of the brain's reward system, also responds to THC, releasing dopamine and creating the characteristic euphoric high. Because this dopamine release is not as strong as with addictive drugs like cocaine or methamphetamine, marijuana tends to have a lower potential for addiction, but repeated overstimulation of this system can still lead to habit formation and, in some cases, dependence. CBD, another major cannabinoid, interacts with the endocannabinoid system differently by modulating the activity of CB1 receptors rather than directly activating them. This is why CBD tends to counteract some of the psychoactive effects of THC and is being studied for its potential therapeutic benefits in anxiety, epilepsy, and chronic pain. The combination of THC and CBD in marijuana products can therefore produce a range of outcomes depending on their ratio, which is why some strains make people feel calm and clear-headed, while others can cause disorientation or intense intoxication. The endocannabinoid system also interacts with other key neurotransmitter systems, including GABA, glutamate, and serotonin, which further influences mood regulation and brain state. This crosstalk is part of why marijuana has such a broad and complex set of effects, reaching beyond just intoxication to impact appetite, immune function, and even reproductive hormones. Scientists are still learning about the long-term adaptations of this system in response to repeated cannabis use, but what is clear is that THC mimicry of natural endocannabinoids is the central mechanism by which marijuana affects both the brain and body in the short term. THC effects on mood, memory, and motivation are among the most noticeable and widely discussed outcomes of marijuana use, and they can be both positive and negative depending on the person, the dose, and the frequency of use. When THC binds to CB1 receptors in brain regions involved in emotional regulation, it can produce a sense of calm, euphoria, and even a heightened appreciation of sensory input like music or food. This is why many people describe marijuana as relaxing or even meditative. The amygdala, which helps process fear and threat detection, is one of the main targets of THC, and its altered activity can make stress feel less overwhelming. For some, this reduction in amygdala reactivity leads to a decrease in anxiety. However, if the dose is high or the individual is predisposed to anxious tendencies, THC can actually amplify amygdala activity and trigger paranoia or panic attacks, creating a very different experience. This dual effect helps explain why marijuana can be therapeutic for some but uncomfortable or even distressing for others. Memory is also strongly influenced by THC because of its action on the hippocampus, the brain's primary center for forming new memories. Under the influence of marijuana, the hippocampus becomes less efficient at encoding and storing new information, which is why users often forget conversations or tasks shortly after they occur. This disruption is usually temporary, wearing off after the effects of THC subside, but repeated use can interfere with learning processes if marijuana is consumed daily or in large amounts. Long-term heavy users have been shown in some studies to exhibit changes in hippocampal volume and function, though many of these effects seem to reverse after a period of abstinence. The short-term memory impairment that marijuana causes is one of the reasons it is discouraged before activities that require focus and attention, like studying, driving, or operating machinery. Motivation is affected in a slightly different way because THC influences the brain's dopamine pathways, particularly in the mesolimbic system, which is associated with goal-directed behavior and reward anticipation. When THC activates CB1 receptors in this circuit, dopamine release increases temporarily, creating feelings of pleasure and satisfaction. This can make ordinary activities feel more enjoyable and rewarding in the moment. However, if cannabis use becomes chronic, the brain can downregulate its natural dopamine signaling, leading to blunted motivation over time. This is sometimes referred to as amotivational syndrome, a condition where individuals find it harder to initiate tasks or pursue long-term goals. While this phenomenon is still debated in research, evidence suggests that heavy, prolonged use, especially starting in adolescence, can alter the brain's reward sensitivity in ways that reduce drive and persistence. Another important aspect is how marijuana impacts the prefrontal cortex, which governs executive functions like planning, decision making, and impulse control. THC temporarily dampens activity in this area, which can make users feel more creative or spontaneous, but can also impair their ability to weigh consequences or make sound judgments. This explains why people might make impulsive choices under the influence or find it harder to stay on track with responsibilities. The interaction between prefrontal cortex changes, dopamine modulation, and hippocampal disruption creates a complex picture of how marijuana influences overall cognitive performance and goal-directed behavior. The combined effect on mood, memory, and motivation is why marijuana can be such a mixed experience. For someone under stress, it can provide relief and even improve well-being in the short term. For someone who needs to learn, concentrate, or stay disciplined, it can become a hindrance. Understanding these brain mechanisms helps explain why marijuana is used recreationally by some, medicinally by others, and avoided entirely by people who find its impact on their cognition and motivation disruptive. THC has a significant impact on sleep and circadian rhythms because of its interaction with the endocannabinoid system, which plays a key role in regulating the sleep-wake cycle. When marijuana is consumed, THC activates CB1 receptors in brain regions that control arousal and sleep initiation, often leading to drowsiness and faster sleep onset. This is one of the reasons many people use cannabis to help them fall asleep, particularly if they suffer from insomnia. In the short term, THC tends to reduce the time it takes to enter the first stage of non-REM sleep and can increase total sleep duration. However, it does not affect all stages of sleep equally. One of the most consistent findings in research is that THC decreases REM sleep, the stage of sleep associated with vivid dreaming, memory consolidation, and emotional processing. People who use cannabis regularly often report having fewer dreams or less intense dreams, which is consistent with this reduction in REM activity. While reduced REM sleep can feel beneficial to people who experience nightmares or intrusive dreams, such as those with PTSD, chronic suppression of REM over long periods might interfere with optimal brain function. REM sleep is believed to play a crucial role in regulating mood, problem-solving, and integrating memories. When someone stops using marijuana after long-term use, they often experience what is called REM rebound, where dreaming becomes intense and vivid for several nights, sometimes accompanied by restless sleep. This suggests that the brain attempts to compensate for the lost REM cycles during cannabis use, emphasizing how important this stage is for overall mental health. THC effects on slow-wave sleep or deep sleep are more complex. Some studies suggest that moderate doses may increase the proportion of deep sleep, which is the most restorative phase of sleep responsible for physical repair, immune function, and growth hormone release. This could explain why some users report waking up feeling more refreshed after using cannabis at night. However, higher doses or chronic use may fragment deep sleep and lead to poorer overall sleep architecture, leaving users feeling groggy or fatigued upon waking. The dose-dependent nature of these effects is one reason why people have such varied experiences using cannabis as a sleep aid. Circadian rhythms, which are the internal 24-hour cycles that regulate sleep and wakefulness, hormone release, and metabolism, can also be influenced by marijuana. THC has been shown to shift circadian timing in some studies, meaning it can alter when the body naturally feels sleepy or alert. This can be helpful for people whose circadian rhythms are out of sync, such as those with delayed sleep phase disorder, but it may also contribute to irregular sleep patterns if used inconsistently. Nighttime cannabis use might promote falling asleep earlier, while daytime use could interfere with alertness and productivity by creating residual sedation. Over time, this disruption can lead to desynchronization of the circadian system, which is associated with poorer mood regulation, reduced cognitive performance, and metabolic issues. CBD, another compound in cannabis, interacts differently with sleep. Unlike THC, CBD is not sedating at typical doses and may actually promote wakefulness in some individuals. Interestingly, when combined with THC, CBD can reduce some of THC's sedative effects and may lead to a more balanced sleep profile. This is why certain cannabis products are marketed with specific ratios of THC to CBD, depending on whether the goal is to encourage sleep or maintain daytime clarity. Because the endocannabinoid system naturally regulates both arousal and sleep, frequent cannabis use can cause the brain to adapt by reducing its own production of endocannabinoids. This can make it more difficult to fall asleep without cannabis, leading to a cycle of dependence for sleep maintenance. Understanding these effects is crucial for using marijuana strategically rather than habitually, so that it supports rather than disrupts healthy sleep patterns. When marijuana is used, its short-term effects on the brain are largely driven by THC's ability to bind to CB1 receptors and temporarily change how neurons communicate. This rapid alteration in signaling leads to the familiar effects of intoxication, such as euphoria, altered perception of time, relaxation, increased appetite, and impaired coordination. The hippocampus, prefrontal cortex, and basal ganglia are particularly sensitive to this shift, which is why memory, decision, making, and motor function can all be affected within minutes of consumption. Reaction times slow down, short-term memory becomes less reliable, and attention may wander. These effects usually last a few hours and then wear off as THC is metabolized and CB1 receptor activity returns to baseline. During this acute phase, dopamine release in the reward system is elevated, contributing to the pleasurable high, while GABA and glutamate signaling are modulated, producing the sense of calm or mild sedation many users describe. Short-term changes also include physiological effects such as increased heart rate, blood vessel dilation, and slight drops in blood pressure, which together create the classic red eye appearance. Some individuals experience heightened sensory perception or intensified emotional states, which can feel enjoyable but occasionally result in anxiety or paranoia if the dose is high. These immediate effects are dose-dependent, meaning that a small amount may produce mild relaxation, while a large amount can lead to disorientation, confusion, or even acute panic. Importantly, short-term changes are generally reversible, and once the substance is cleared from the body, cognitive and motor functions typically return to normal. Long-term brain changes from repeated marijuana use are more complex because the brain adapts to the consistent presence of THC by adjusting its own signaling systems. Chronic exposure can lead to downregulation of CB1 receptors, meaning the brain reduces the number or sensitivity of these receptors to maintain equilibrium. This adaptation can blunt the intensity of the high over time, which is why frequent users often need larger doses to achieve the same effects, a process known as tolerance. Once cannabis use stops, it can take several weeks for CB1 receptor density to return to baseline levels, during which time people may experience irritability, sleep disruption, and decreased appetite as part of withdrawal. In terms of structure and function, some studies using brain imaging have found that heavy, long-term cannabis users, especially those who started in adolescence, show differences in the volume and connectivity of areas like the hippocampus and prefrontal cortex. These regions are critical for memory formation, attention, and executive control, and their alteration may contribute to subtle but measurable deficits in cognitive performance. Other studies have suggested changes in white matter pathways that connect different brain regions, which could impact processing speed and coordination between neural circuits. However, there is ongoing debate about whether these changes are permanent or reversible after sustained abstinence, with many findings showing at least partial recovery of brain function after several months without use. Long-term use can also affect emotional regulation and motivation because of its impact on the brain's dopamine system. When dopamine signaling becomes chronically overstimulated by THC, the brain compensates by reducing baseline dopamine production, which may lead to reduced motivation and a blunted sense of reward from everyday activities. This is part of the mechanism thought to underlie amotivational symptoms in some heavy users. The effect is not universal, but it is more pronounced in people who begin using cannabis heavily during their teenage years when the prefrontal cortex is still developing. The distinction between short-term and long-term changes highlights why occasional marijuana use has a very different risk profile from chronic, heavy use. Short-term effects are mostly transient and predictable, whereas long-term effects involve neuroadaptations that can persist beyond the period of intoxication and potentially influence cognition, mood, and behavior for weeks or months after stopping. Not everyone experiences marijuana the same way, and the differences in response are influenced by a combination of genetics, brain chemistry, environment, and prior experience with cannabis. One major factor is genetic variability in the enzymes that break down THC, particularly the liver enzyme CYP2C9. People with slower variants of this enzyme metabolize THC more slowly, which means the psychoactive effects last longer and can feel more intense, even from a small dose. Conversely, fast metabolizers may process THC quickly and feel less of an effect, leading them to consume more to reach the desired state. These metabolic differences can explain why one person might feel relaxed after a single puff while another feels overwhelmed or anxious from the same amount. Brain receptor density also plays a significant role. The number and distribution of CB1 receptors in the brain vary naturally between individuals, and this determines how strongly THC can bind and exert its effects. Someone with high CB1 receptor density in the hippocampus might notice stronger memory disruptions, while another person with fewer receptors in that region might experience only mild cognitive effects. Similarly, genetic differences in the Fa enzyme, which breaks down the body's own endocannabinoids, can influence baseline endocannabinoid tone and therefore affect how external cannabinoids like THC are perceived. People with lower Fa activity may already have higher natural levels of endocannabinoids, meaning that adding THC can push their system into overstimulation, sometimes leading to anxiety or paranoia. Tolerance is another important factor shaping individual responses. Frequent cannabis users often report feeling less intoxicated from the same amount of THC than someone who uses infrequently. This is because repeated exposure leads the brain to downregulate CB1 receptors, effectively dampening the overall response. Occasional users, by contrast, have a more sensitive endocannabinoid system and tend to feel stronger effects, even from low doses. This difference is particularly noticeable when switching methods of consumption. Someone who is tolerant to smoking may still feel unexpectedly strong effects from edibles, since THC is metabolized differently when ingested and converted to 11-hydroxy-THC, a more potent psychoactive metabolite. Psychological state and environment can also dramatically shape the cannabis experience. Being in a comfortable, safe setting with trusted people often enhances relaxation and enjoyment, whereas using marijuana in an unfamiliar or stressful environment can trigger anxiety. The concept of set and setting, often discussed with psychedelics, applies here as well. Expectations play a role too. Someone anticipating a calming experience is more likely to interpret bodily sensations as pleasant, while someone who fears losing control might perceive the same sensations as threatening. Age and develop. Mental stage influence cannabis response in important ways. Adolescents and young adults are more vulnerable to the cognitive and emotional effects of marijuana because their prefrontal cortex and reward circuits are still maturing. This means that cannabis use during adolescence can have a stronger effect on motivation, risk-taking, and memory compared to use in adulthood. Hormonal fluctuations may also affect response, with some research suggesting that estrogen levels can influence CB1 receptor sensitivity, making females more sensitive to the effects of THC at certain times in the menstrual cycle. Finally, the chemical composition of the cannabis product itself is a major determinant of individual experience. High THC strains with little or no CBD are more likely to cause anxiety or paranoia, while strains with a balanced THC to CBD ratio may produce a smoother, more controlled high. Terpenes, the aromatic compounds in cannabis, can also modulate the experience by interacting with neurotransmitter systems. Some terpenes promote relaxation, while others increase alertness. This is why two products with the same THC percentage can feel very different. The diversity of responses highlights that marijuana's effects are not one-size-fits-all and must be understood in the context of biology, psychology, and environment. Appreciating these factors is key to predicting how cannabis will affect an individual and using it in a way that aligns with their goals and tolerances.